Have you ever played a game against an AI, maybe chess or even just tic-tac-toe, and it just feels unbeatable? Like it knows what you're going to do before you do? Well, it's not magic. There's a secret to that perfect play. And today, we're going to pull back the curtain on this simple, brilliant logic that makes it all tick. So, let's kick things off with a little thought experiment. Picture this. You're standing at the entrance to a maze. You know that every single path leads to a prize, but all the prizes are different. Your mission, should you choose to accept it, is to walk out with the absolute best one. How do you guarantee you find it? Now, your first instinct might be to just, pick a path and hope for the best. But if you want to be sure you get the best prize, there's a much smarter way. It's a bit counterintuitive, but it's an incredibly powerful way of thinking that we're going to walk through right now. Yeah, you heard that right. Instead of making a blind guess at the very beginning, the truly perfect strategy is to start at the end and work your way backwards. I mean, think about it. How can you make the right choice at a fork in the road if you don't know where each of those paths is going to take you? So here's the playbook. You follow one path, just one, all the way to the end. You check out the prize. Then, and this is the absolute key, you backtrack. You go back to the last fork you passed. From there, you explore the other path from that same fork. Once you know the prize down both paths, you can confidently say, okay, from this specific junction, this is the path to the better prize. You just keep repeating that process, working your way back from the end, solving the maze one decision point at a time. Okay, so you've got that down. Now let's throw a wrench in the works. What happens if you're not the only one in that maze? This is where it gets really interesting. Imagine that at certain forks in the road, you don't get to choose, an opponent does. And this opponent has one goal and one goal only, to mess you up. They're going to look at the options ahead and deliberately push you down the path that leads to the absolute worst prize for you. This sets up this awesome strategic battle. You are now the maximizer. Your goal is always to get the highest score you can. Your opponent is the minimizer, and they're doing everything in their power to stick you with the lowest possible score. It's a constant tug of war. And here's the mindset you have to adopt for this to work. You can't just hope your opponent makes a mistake. Nope. You have to assume they are a perfect player, just as smart as you are. You have to plan around the fact that they will always make the best move for them, which, by definition, is the absolute worst move for you. So this whole thing with a maze and an opponent trying to sabotage you, what does that have to do with AI? Well, it turns out it's everything. This whole process of you trying to maximize your outcome while assuming your opponent is trying to minimize it, that is exactly how a game-playing AI thinks. See, to an AI, a game of chess isn't really a board with wooden pieces. It's a gigantic, sprawling decision tree. But honestly, you can just think of it as our maze. Every fork in the road is a possible move, and every single path leads to a final outcome, a win, a loss, or a draw. And the name for this maze-solving strategy is the Minimax Algorithm. Now, the definition says it's recursive. That word can sound a little intimidating, but all it really means is that it repeats the same simple logic over and over. Remember in our maze how we'd go to the end, backtrack, and evaluate one junction? The algorithm just does that again and again and again, working its way all the way from the final scores back to the very first choice. All right, enough talk. Let's walk through a super simple example. The prizes at the end of our paths, they're now just scores. Let's call them utility values. A high score is a win for us. We're the maximizer. A low score, well, that's what our opponent, the minimizer, is trying to stick us with. Okay, so we always start at the end, at the bottom. At this first junction, it's the minimizer's turn to pick. They look down the two paths and see the possible final scores, a 3 and a 5. So what do? Their entire job is to minimize your score. What's worse for you, a 3 or a 5? The 3, of course. So they choose that path. That decision gets locked in, and the value of 3 effectively gets passed up to the level above. From now on, that entire branch of the maze is just worth 3. Now we hop over to the next junction on that same level. Here, it's the minimizer's turn again, but they're looking at different outcomes, a score of 2 and a score of 9. And again, it's a no-brainer for them. They want to give you the lowest score possible. So between a 2 and a 9, they're absolutely going to force you toward the 2. That choice gets locked in, and the value of 2 gets passed up. Okay, now we've worked our way back to the top level. It's our turn to make a move, and this is where it all comes together. The critical thing to realize is that we are not choosing between all 4 numbers at the bottom. We're choosing between the outcomes that our perfect opponent has already guaranteed for us. Our choice is actually really simple now. Do we go down the path that we know will end in a score of 3, or do we go down the path that we know will end in a score of 2? Well, we're the maximizer. We want the highest value possible, so we choose 3. And that's it. By working backwards and assuming our opponent is a genius, we just found the guaranteed best move from the start. So this method is incredible. It literally guarantees the perfect choice every single time. But as you can probably imagine, that kind of perfection comes at a pretty steep price. And this really gets to the heart of the Minimax trade-off. The upside is amazing. You are guaranteed to make the optimal move. For a small game like Tic-Tac-Toe, it's flawless. But the downside is a monster. To get that guarantee, the AI has to explore every single possible move. And for a complicated game, that number is just mind-bogglingly huge. This is what folks in computer science call time complexity. All you really need to know is that the amount of work the AI has to do doesn't just add up, it grows exponentially. It explodes. To put that into perspective, for a game like chess, the number of possible board setups is greater than the number of atoms in the known universe. You can't check them all. It's not possible. So even though pure Minimax is way too slow for giant games, its core logic is the foundation for AI in almost every two-player strategy game you can think of. Modern chess engines use really clever tricks to prune the tree, basically to ignore paths that are obviously bad without exploring them. But that fundamental idea is still there. Assume your opponent is a perfect minimizer and work backward to find your best move as the maximizer. And that really leaves us with the ultimate challenge in building game-playing AI. We have a recipe for perfect play, but it is brutally, comically slow. So the big question becomes, how can you get that same perfect logic without having to explore every single dead end in the maze? How can an AI be both perfectly strategic and also smart enough to know which paths aren't even worth looking down? Answering that, well, that's the holy grail.